Picture the solar system as a lively town square. The planets are the regulars who loop the plaza in steady orbits. The comets are the occasional street performers who swing by. And the asteroids are the market stalls that do not move far from home. Then one day, a stranger steps into the square, moving with a confidence that says, "I am not from around here, and I will not be staying long." That is an interstellar object. It is a piece of rock, ice, or something more exotic that formed around another star, wandered for ages through the deep quiet between suns, and now slices through our sky like a postcard thrown from a speeding train. Our traveler's name is 3IATLAS, and the 3 tells you it is only the third such visitor ever confirmed. In cosmic terms, we are witnessing a rare drive-through from beyond the neighborhood watch. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes it's best enjoyed the way you'd enjoy a late-night conversation, quietly with a cup of tea and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. So what makes an interstellar object different from a local comet or asteroid? Homegrown wanderers are bound to the sun, even when their paths are stretched like taffy. Gravity tugs them into loops. They may take centuries to return, but return they do. An interstellar object is built different. It arrives already moving faster than the sun can hold. Think of gravity as the ultimate bouncer and interstellar objects as guests who already have momentum that exceeds the cover charge. They curve as they pass the sun because everything curves around gravity, but they never settle. Their path is a one-time arc that bends and then opens back out. A hello that immediately turns into goodbye. This is why we call it a one-time flyby. Blink too slowly, and the guest has crossed the dance floor, winked at the camera, and slipped out the far door. The name 3IATLAS says two things. First, the I marks it as interstellar. Second, Atlas credits the survey that raised its hand and said, "Hey, there is a new object with outsider vibes." Surveys are the patient night guards of the sky. They take long, repeated looks, comparing each image to the last, like a flipbook for motion. When a point of light refuses to behave like a local, the alarms go from polite to interesting. That is what happened here. A spot moved just a bit wrong, and that wrong turned into a story. Let us talk about the motion, because this is where the personality of an interstellar object really shows. If you could draw its path, you would see a sweeping curve that is not a closed loop, no tidy circle, no stretched oval. Instead, it is a wide, open swoop. Imagine throwing a ball past a campfire. The ball's path curves toward the glow as heat shimmers the air, but it does not fall in. It bends. It thanks the fire for the warmth, and it keeps going into the night. Replace warmth with gravity, and you have the basic idea. The sun pulls, the object bows, and then it continues on. Destination unknown, itinerary flexible. Because 3IATLAS was born under another star's rules, its surface materials may not respond to sunlight the way our local comets do. Some grains may darken instead of brightening. Some ices may release gas at different distances, and some colors may hint at chemistry learned in a different stellar classroom. We will save the deep dive on those clues for later, but keep that possibility in your pocket. It is like hearing an accent in a crowded room. You do not need the biography to know this person grew up somewhere else. Catching an interstellar visitor is hard, not because the sky is stingy, but because the sky is enormous. These objects are small compared to planets, often darker than a politician's sunglasses, and moving quickly against fields of stars that do not budge. Tracking them demands fast coordination between telescopes on the ground and instruments in space. Once the alert goes out, observers sprint, because every hour matters. The object is changing its relation to the sun and Earth with each tick of the clock. You schedule time on a telescope, aim, and hope the weather and the computer and the universe all agree to be kind for a few precious minutes. Space loves to keep us humble. 3IATLAS also gives us a chance to rethink our travel brochures for the galaxy. The way it shines, the way it fades, the way dust or gas might lift from its surface. All of these are clues to the temperature and radiation environment where it grew up. If it carries weirdness in its makeup, that weirdness is not random, it is a map back to its birthplace. We cannot follow it home, but we might read the return address. Black holes are the universe's way of saying delete browsing history permanently. Interstellar objects are the universe's way of sending vague postcards that say wish you were here in a handwriting. We are still learning to read. Why should you care? Beyond the thrill of a rare catch. Because a single outsider can test our ideas about how planets form, how small bodies evolve, and how common or uncommon certain materials are in other star systems. If 3 visitors have already passed within a human lifetime, then the galaxy may be scattering these crumbs all the time. And if crumbs are common, then so is the chance to sample other stellar kitchens. It is like discovering that your quiet street is actually on a scenic route. Suddenly, you look at the traffic with fresh eyes. Finally, think about the sheer romance of it. A rock or an icy shard, forged far from our sun, set loose by some long-ago gravitational shuffle, wandering for ages, and then, for a brief and brilliant moment, crossing our sky. It does not care about our calendars or our pride. It will not orbit for our convenience. It arrives, it bends, it leaves, and in between it whispers a few secrets into our detectors. The moment is fleeting, but the lesson is lasting. Next up, we follow whispers in the dark, tiny clues that might stretch behind our traveler like breadcrumbs in vacuum. If there is a trail of oddities, Chapter 2 will learn to see it. Chapter 2. The Case of the Cosmic Breadcrumbs. What counts as an anomaly? Imagine the solar system as a vast museum after hours. The galleries are quiet, the planets sit in their frames, and the usual motion of dust and charged gas is the security staff doing their routine rounds. Then a visitor walks through, and somehow, the next morning, the logs show smudges on the glass, a light left on in a hallway, and a floor sensor that blinked for a moment at 2 in the morning. Nothing is broken, nothing is stolen, but something is off. That word off is where anomalies live. Let us define the term in plain language. An anomaly is a measurement that does not match what long experience says should happen in the same place under the same conditions. Think of a star field that always dims and brightens in a gentle rhythm, and suddenly a narrow patch glows a little more than expected. Picture a region of space that usually hums along at a steady temperature, and for one night it reads slightly warmer, like a stovetop that should be cold but is faintly warm to the touch. Or consider tiny particles of dust and threads of charged gas that generally drift with the solar breeze, and for a short window they wobble as if nudged by an unseen hand. These are the breadcrumbs. Each crumb is small and easy to dismiss. The power appears when several crumbs line up in space and time. Strange lights sounds dramatic, but most of the time we are talking about subtle changes in brightness, too small for the eye. Telescopes take images in carefully timed sequences, the way a wildlife camera snaps frames along a trail. Analysts then compare frame after frame, subtracting last night's view from tonight's. When a patch that should be calm shows a gentle rise or fall that cannot be explained by the angle of sunlight, by known dust clouds, or by instrument noise, it enters the anomaly notebook. It is not proof of anything on its own. It is an invitation to be curious. Curiosity is the interest rate on the bank account of wonder. It compounds quickly if you keep paying attention. Odd warming is another breadcrumb. Space may feel like it should be one big freezer, but even the emptiest regions are not perfectly even. Instruments that sense heat can map faint differences like a thermal weather report. When an area that is typically mild registers a brief uptick, investigators ask, did the sun hiccup in a way we already understand? Did we look through a thicker patch of dust than usual? Did the sensor itself stretch after a long night, like a human reaching for coffee? Only after crossing off the usual suspects does that warm pixel earn a sticky note that reads, "Watch." Then there are the tiny motion quirks. Dust and charged gas do not just sit there, they are constantly nudged by sunlight, by the electric and magnetic fields that thread outward from the sun, and by gravity from everything with mass. That constant nudge creates patterns that are surprisingly reliable when averaged over time. If a cluster of grains shifts in a way that resists those expectations, even for a short while, it is like a flock of birds veering when there is no wind gust. You might not know why, but you can measure that it happened. Physics is the universe's very firm no-refund policy, which is why these deviations are valuable. They either teach you something new or remind you that your model needs a tune-up. Here is where the mystery gets good. Imagine drawing the expected path of our interstellar visitor across the sky, not as a thin line, but as a corridor, a moving lane that accounts for observational uncertainty. Now place each anomaly on a map with a timestamp. One odd glow might be nothing. One warm pixel might be the observational equivalent of a sneeze. One wobble might be a software gremlin. But if 3 different kinds of crumbs appear inside that moving lane, spaced in a way that tracks the traveler's progress, your eyebrow goes up. It is the difference between a random cluster of footprints in a park and a set that points in a single direction with the stride of a purposeful walker. Of course, pattern-hungry brains love stories, and that is both a strength and a trap. The job is to make a story earn its plot. So teams set rules before the search begins. For example, do not count an odd glow unless it persists longer than a single frame. Do not trust a warm pixel unless a different instrument sees a similar bump. Do not mark a motion quirk unless independent observers spot it as well. The art is to be patient without becoming numb. Entropy likes mess. The trick is to separate interesting mess from ordinary clutter. You might wonder how tiny is tiny. Think smaller than a camera shake, subtler than the flicker of a candle in a quiet room. Instruments help, but so does choreography. Multiple observatories coordinate to watch overlapping patches of sky. When one team sees a brief brightening and sends a quick note, another team pivots to cover the same spot. It is like a relay race, where the baton is a patch of darkness that for a heartbeat refuses to behave. Space is big, and the lost and found desk is even bigger, so the coordination matters. One of the unsung heroes of anomaly hunting is time itself. A single snapshot is a rumor. A timeline is a testimony. By layering measurements, you can tell whether an anomaly drifts with the same speed and direction you would expect if it were riding near the interstellar visitor. If it lags, leads, or sits alongside the projected corridor, the case strengthens. If it wanders away like a bored tourist, you let it go. The universe is generous with distractions. Another ingredient is language. Investigators avoid words that make promises too soon. Instead of saying signature, they might say feature. Instead of proof, they say evidence. It keeps the conversation honest. It also keeps room for surprises, because sometimes a cluster of anomalies that looks like a path turns out to be 2 unrelated stories passing on the same street. Coincidence is the magician of the cosmos. It loves to practice new tricks in the corner of your eye. Why assemble all these crumbs at all? Because if a trail exists, it does more than point to a traveler. It describes how that traveler interacts with its temporary neighborhood. Does it drift through like a ghost, barely noticed? Or does it borrow the air, stir the dust, and leave a faint echo in its wake? Answering that is not just poetry. It makes better predictions for the next outsider. It teaches us how sensitive our instruments really are. It sharpens our sense of normal, so that the next off moment stands out faster. So that is the case file. Faint glows that rise and fade, warm spots that do not belong, and tiny motions that seem to wink out of rhythm. When enough of them line up along the projected route, the museum guards of the sky lean forward in their chairs. Something walked these halls. We cannot yet say what it carried or why it moved the way it did. But the footprints do not match any shoes in our closet, and that is reason enough to turn on the lights and look again. Next, we will step into the breezy world where charged gas gets moody and the solar wind forgets its manners. Chapter 3: Sky Traffic. But with plasma, space weather gets fussy. Picture a river that never stops. It flows day and night, winter and summer, crossing valleys you cannot see. That is the solar wind, a steady stream of charged particles rushing outward from the sun, carrying with it the sun's invisible magnetic handwriting. Most days, this flow behaves like a calm highway at dawn. Speeds vary within a familiar range, the direction holds steady, and the magnetic lines thread through space in graceful spirals. Predictable does not mean boring. It means the current follows rules we have learned to read. Then, every so often, the river stutters. A patch gets choppy. The magnetic writing tilts, pauses, or scribbles a flourish. Somewhere, the space equivalent of a traffic app starts pinging. Space weather is the group chat of the universe, always pinging at the worst time. To understand why those pings matter, start with how order usually looks. The solar wind leaves the sun hot and busy, but by the time it sweeps past Earth, it is settled into lanes. There are fast lanes from coronal holes, slow lanes from quieter regions, and transitional zones where the two mix like warm and cool currents in the sea. Embedded in all that are magnetic fields that behave like guide rails. Charged particles tend to follow these rails, spiraling along them, the way hikers stick to switchbacks on a steep slope. Instruments on satellites sample the stream second by second, counting particles, checking their energy, and watching the magnetic field tilt and twist. Over years, you build a baseline, a sense for what a normal day looks like in each lane and season. Now bring in the fuss. Small, localized ripples can show up as brief changes in particle density, tiny swings in temperature, or sudden kinks in the magnetic direction. Most of the time, the sun itself flips the switch. A tiny jet in the corona, a wrinkle in the outflow, a shock wave from a more distant eruption. But space is not a single-source play. The river flows through a landscape crowded with dust grains, ancient tales from old comets, and occasional swarms of particles freed by sunlight. These ingredients do not stop the wind, but they can roughen its surface. Imagine fine sand thrown into a breeze. The air still moves, yet the texture shifts. Here is the question that makes scientists lean closer to their monitors. Could an entourage around 3IATLAS be adding its own grit to the stream? Not a dramatic storm, just a traveling patch of texture. Start with daylight. Sunlight strips electrons from the thinnest skin of dust grains, leaving them slightly charged. The grains respond to both the breeze and the magnetic guide rails, drifting differently than neutral specks would. If enough grains gather, they can create a pocket where the wind's charged particles scatter more than usual, like raindrops hitting a swarm of tiny bubbles. The result is a ripple you might measure as a quick increase in turbulence or a momentary bend in the magnetic direction. Another player in this scene is gas released from the visitor itself. Even if that release is quiet, a whisper of molecules can be torn apart by light, creating newborn charged fragments. These newborns are like kids hopping onto a moving walkway. At first, they lag. Then the magnetic rails grab them, and they are whisked along, while still learning the flow. That pickup process steals a little energy from the wind and shakes the rails. Downstream, an instrument could register that as a shallow dip in speed, or a subtle warming as the flow reorganizes. Nothing catastrophic, but noticeable if you know the rhythm. How small are we talking? Think of ripples that last minutes or an hour, stretching across a region no larger than the distance between a planet and its moon. In the language of instruments, that is long enough to sample and large enough to compare across platforms. A satellite near Earth might catch a flicker. A spacecraft closer to the sun could sense an earlier echo. A probe a bit off the ecliptic might miss it entirely, which is a clue by itself. Triangulation in space is like listening to thunder from 3 hills. The delays and the loudness tell you where the lightning happened, or whether there was lightning at all. There is also the shape of the magnetic writing to consider. When a moving obstacle enters a magnetized flow, field lines can drape around it like streamers catching on a car mirror. If 3IATLAS carries a cloud of dust and ionized gas, even a thin one, you can imagine the magnetic rails bending slightly as they slide past. The drape would not be a neat bow. It would be an asymmetrical, shifting veil whose edges flutter with the current. Instruments might see the field tilt one way, hold for a short stretch, then relax. If you plot that tilt against time and the visitor's projected path, a match would make hearts race and coffee mugs empty. Of course, you must separate real fuss from false alarms. Instruments are sensitive. A satellite passing from sunlight into shadow can twitch. A high-energy particle sneaking into a sensor can fake a spike. Ground controllers know these gremlins and account for them by cross-checking different measurements. If the particle counter flares but the magnetic field stays calm, chalk it up to a local hiccup. If both twitch together with the right timing, your eyebrows earn their lift. Let us play out a vivid what-if. Suppose a cluster of sensors records a brief patch where the wind grows more turbulent and the magnetic field leans, all while a dust detector on a different craft tallies a few more impacts than usual. The timing lines up with the corridor where the interstellar visitor is cruising. That would not prove cause. It would, however, push the community to arrange follow-up coverage along the path ahead, the way bird watchers spread out along a flyway after the season's first sighting. If a second ripple shows up with the same character and timing, the case for a traveling texture strengthens. Why does this matter beyond the thrill? Because every ripple is a free experiment. It teaches us how the solar wind interacts with moving, charged clouds in real conditions, not just in simulations. It reveals how sensitive our monitors are and where they need upgrades. And it hints at a larger truth. Space is not empty. It is a living weather system with lanes, eddies, and surprise squalls. Understanding that system helps protect satellites, guides deep space navigation, and tells us how outsiders, even quiet ones, share the road. So yes, the universe keeps pinging at awkward moments. The notifications can be annoying, but in those buzzes is a map of a restless sky, and maybe, just maybe, the soft signature of a traveler passing through with a pocket of electrified confetti swirling in its wake. Chapter 4, Glitter That Talks, Dust Grains as Messengers. If you have ever walked through a sunbeam and watched motes swirl like confetti, you already know a secret of the cosmos. Tiny bits can carry big stories. Around wandering objects, dust is not just debris. It is a messenger service with a flair for dramatic lighting. Grain size, spin, and the stuff they are made of decide how sunlight is scattered, which is why faint halos appear in some angles and razor-thin tails leap out at others. The show is quiet, but the script is rich. Start with size. A grain as small as a smoke particle treats sunlight differently than a grain as large as beach sand. Smaller grains tend to bounce light forward, sending a narrow spray along the direction of the sun's rays, which can make a shy, glowing halo when you look from just the right angle. Larger grains reflect more broadly, brightening a tail that fans behind like a banner in slow motion. Think of it as a chorus line where the short dancers whisper to the spotlight and the tall dancers wave to the balcony. When a halo pops into view only near a specific angle from the sun, that angle is a clue, a ruler made of glow. Now add spin. Grains do not just drift, they twirl. Sunlight can nudge them into rotation, and so can collisions or electric charges picked up in the solar breeze. A spinning grain presents changing faces to the light, like a tiny disco ball that forgot to file for a noise permit. If the grain is uneven or flaky, its twirl can produce a faint, rhythmic shimmer that telescopes can measure as a pattern in polarization, which is a fancy way of saying the light has a preferred direction to its wiggle. That pattern encodes whether grains are round, elongated, or shaped like little shingles. Space loves variety. Somewhere out there is the dust equivalent of a drawer full of mismatched socks. Composition is the voice. Silicate minerals, carbon-rich soot, salty ices, and complex organics each speak light in their own dialect. Some absorb blue more than red, painting the dust in warmer shades. Others reflect with a neutral tone, like a polite grey that refuses to join the argument. A few materials glow softly in the infrared, a kind of after-hours whisper we can listen to with detectors that feel heat rather than see light. When observers split the light and map its colors, they are building a fingerprint of the dust population. It is the difference between hearing a crowd and recognizing individual accents in the hum. Now imagine grains that were forged around a cooler star, perhaps a dim red sun, where the furnace runs gentle and long. In that neighborhood, different minerals can form, including exotic silicates with iron mixed in unusual ways, or ices that trap fragile molecules like a time capsule. When such grains wander into our sunlight, they may refract and reflect in unfamiliar patterns, bending light like tiny stained glass windows floating in darkness. The panes are not painted by artists. They are painted by atomic structure. Change the structure, change the color story. If that stained glass effect skews the halo toward a surprising hue, it becomes a signpost pointing back toward a colder nursery. There is also shape, the wild card. Perfect spheres are rare in the real world. Many grains are lumpy, porous, or jagged, more like frosted cornflakes than marbles. Porous grains scatter light with a soft touch, creating halos that look fuzzy at the edges. Compact, glassy grains scatter with a crisper edge, sharpening the tail like a pencil line. And if magnetic minerals hide inside, those grains can try to align with the solar magnetic field, producing a faint order in their dance that shows up as a polarization signature. It is as if the chorus line suddenly agrees on a footstep, and for a heartbeat, the stage looks choreographed. Here is a quiet superpower of dust. It can reveal motion you cannot otherwise see. When the visitor sheds grains at a steady rate, the sizes drift into separate lanes. Tiny grains are pushed harder by sunlight pressure, sweeping away into broad, delicate veils. Larger grains lounge closer to the original path, tracing a spine down the center of the tail. If you take images night after night, you can watch this sorting happen, like a time lapse of autumn leaves floating down a stream. From that sorting, you back out the sizes, the release times, and even the rhythm of the shedding. The dust is writing timestamps in light. There is a flavor dimension too. Some grains carry complex organics. They do not announce themselves with neon signs, but they leave gentle hints in the way they reflect and warm. Others include metal-rich inclusions, tiny nuggets that deepen the color or add a sparkle at specific angles. If a passing beam reveals those sparkles consistently, it suggests a mix different from the usual neighborhood recipe. Space is a serious place, but even it enjoys a little glitter when the spotlight hits. And because the universe loves crossovers, dust can talk to charged gas. When grains pick up electric charge, they respond not only to sunlight and gravity, but also to the invisible rails of the solar magnetic field. That means the shape of a dust halo can warp slightly as it drifts through different magnetic neighborhoods, adding a twist to the expected geometry. Detect that twist, and you have learned something about both the grains and the field they are surfing. All of this matters because light is the one messenger that never asks for a ride. It leaves the grains, crosses the dark, and lands in our cameras carrying news about size, spin, and composition. If the news headline reads "Unusual minerals from a cooler star," we will know it not because anyone told us, but because the halo leaned a little warmer, the tail sharpened a little more, and the polarization whispered that the grains are flaky, not round. The message is subtle, like hearing the softest note in a symphony. Yet once you learn the tune, you cannot unhear it. So when a faint glow blooms around a fast traveler, do not call it dust and move on. Call it a conversation. Each mote is a syllable. Each color shift is a verb. And somewhere in that grammar is the origin story of a faraway furnace carried to us by glitter. that learned how to talk. Chapter 5. The gentle push you cannot see. Subtle forces at work. If space had a whisper, it would be the pushes you cannot see. No fireworks, no drum roll, just tiny nudges that change a traveler's path, the way a quiet current moves a leaf on a lake. Our interstellar visitor is not surfing chaos. It is negotiating a world of soft hands. 3 of those hands matter most for our story: gravity, sunlight pressure, and slow vapor release. Each is small on its own. Together, they can leave a pattern that lingers, a trail etched into nearby dust streams like ripples after you skip a stone and watch the circles race outward. Start with gravity, the patient sculptor. Imagine the sun as a heavy anchor in the middle of a wide pond. Everything else, from planets to pebbles, feels its pull. Gravity does not shove, it invites. The path of a passerby curves gently as if bowing to the host before moving on. That much is familiar, but gravity also has texture. Because the pond is not smooth, planets add their own tugs. A giant like Jupiter is a passing tugboat. A smaller world is a rowboat. Even a hefty asteroid is a floating log. As the visitor threads this moving maze, each nearby mass adjusts the curve by a hair's breadth. A near miss with a planet can quicken or slow the traveler like a subtle hand on the back during a crowded exit. Map those micro-courtesies, and you have a choreography written by invisible strings. Now add sunlight pressure, the gentlest shove with the longest reach. Light may seem weightless, but every beam carries a pinch of momentum. When sunlight hits a surface and bounces or gets absorbed, it transfers a tiny push. It is the universe's softest pat on the shoulder. On a polished, bright surface, the pat is a smidge stronger. On a dark, sooty surface, the pat is more like a nudge that warms rather than reflects. Over minutes, that is nothing. Over weeks and months, the accumulated push can shift the track of dust grains and even the parent body by a whisper you can measure. Picture a fleet of invisible thumbtaps, steady and polite, slowly encouraging the traveler toward a slightly different lane than gravity alone would choose. Sunlight, the original wireless charger, with opinions about your trajectory. There is another kind of light push, born from warmth itself. The side of a small body that faces the sun heats up and later re-radiates that heat as low-energy light. That emitted glow also carries momentum, and because the warmest areas are not always evenly spread, the recoil can act like a very weak thruster. Think of it as thermal sighing. Exhale a bit more from one side than the other, and over long stretches you drift. It is not dramatic, it is persistent. Coffee drip, not espresso shot. And then there is slow vapor release, the traveler's tiniest rocket. If the surface holds ices or trapped gases, sunlight can tease out a steady whisper of molecules. They drift away, and by Newton's very stubborn bookkeeping, the body recoils just a little in the opposite direction. Not a jet that flips the craft, more like the faint hiss of air from a pinhole in a tire nudging the wheel ever so slightly as it rolls. The orientation of that hiss matters. If the source faces the sun, the push tends to lean away from the star. If the source hides on a shaded flank, the push can point sideways or even slightly forward along the path. Over time, that creates deviations that an attentive observer can separate from the clean curve gravity would write alone. Now for the fun part, patterns these whispers leave behind. When the visitor sheds dust while under these combined nudges, the grains do not simply trail like crumbs on a straight line. Smaller grains feel sunlight pressure more strongly and peel off into wider arcs. Larger grains stay closer to the spine of the path. Meanwhile, gravity from planets can briefly herd these grains, pulling a section tight like gathering folds in a curtain. Slow vapor release adds a bias, a slight tilt to the whole structure, so that the dust ribbon leans in one direction more than the other. Add it up, and the trail becomes a layered scroll. A central strand of sturdier particles, a gauzy sheet of finer ones, and occasional kinks where a planetary tug or a thermal sigh left its signature. How do these ripples echo into existing dust streams? Picture the inner solar system as a broad, slow river of ancient moats. When a newcomer passes through, even gently, it can imprint waves into that river. One way is by resonance, a fancy word for synchronized nudging. If the traveler's dust crosses paths with a pre-existing stream at just the right timing, gravity keeps whispering in step, adding tiny pushes at the same phase, the way a parent gives a playground swing a tap at each pass. The stream's density can grow a faint crest, a low rolling swell that drifts along its own course long after the visitor has left. Another way is by collisionless stirring. Grains pass near grains, feel each other's gravity for a heartbeat, and diverge by a hair like strangers adjusting shoulders on a busy sidewalk. It is subtle, but a billion subtle shifts can change the texture of a lane. Local electric and magnetic fields can also amplify the pattern, the way wind amplifies ripples on water, though the main actors here remain gravity, light pressure, and vapor recoil. When the dust ribbon bends into a bright arc against sunlight, the angle of that arc tells you which push is winning at that moment. A broader, sunward bow hints at strong sunlight pressure on fine grains. A tail skewed off the expected plane hints that slow vapor release is steering like an unseen rudder. A dogleg or kink at a specific place along the path may point to a planetary handshake. Hello, brief tug, goodbye. All of this is quiet mechanics, but the consequences are loud for anyone trying to read the sky. Miss the gentle pushes, and you misjudge where the debris will be tomorrow. Catch them, and you can forecast the shape of the trail like a weather report for glitter. You can even rewind the pattern to infer when the traveler shed which grains, how quickly it warmed, and how its skin responded to sunlight. The sky keeps a diary. The entries are written in curves. Here is a playful thought. If you could tag each push with a sound, gravity would be a cello, sunlight pressure a steady metronome, and slow vapor release a breathy flute playing off to the side. The music is not obvious when you stand in the orchestra, but step back and the melody emerges. That melody is the trail, a theme that repeats across different lanes of dust, echoing long after the soloist exits stage right. And somewhere far ahead on the score, a new measure waits for the next outsider to add its own soft notes, because in space, even whispers travel. Chapter 6, Alien Freezer Isle, Exotic Ices Without the Symbols. Picture a supermarket in deep space, with lights dimmed and freezers stretching to the horizon. The labels are not in any language we know, but the shelves are fully stocked. That is the vibe of an interstellar object's surface, a cold pantry filled with ices and organic solids that formed under rules set by a different star. Space runs the coldest grocery store, and the return policy is eternity. When we say ice here, we do not just mean frozen water. We are talking about a lineup of substances that turn into gas at different temperatures and sunlight levels. Some, like frozen nitrogen and frozen carbon monoxide, are the sprinters. They do not need much warmth to start escaping. Others, like frozen carbon dioxide, frozen methane, and frozen methanol, take a little more coaxing. Water ice is the marathon runner. It stays put until the sunlight is strong and steady. On a traveler born around a cooler, dimmer star, the mix could be rearranged. Imagine a crust layered like a cake, baked in reverse, delicate flavors near the surface, sturdy flavors deeper down. There is also the question of texture. Not all ice is the same. Some forms are glassy and disordered, like frost blown onto a window in a sudden chill. That kind of glassy ice can trap other molecules inside, holding them the way a sponge holds water. Warm it slightly, and the structure relaxes, releasing the guests in slow motion. Other forms are orderly, with molecules lined up neat as tiles. Those are less welcoming to hitchhikers. If an interstellar object carries both textures in stripes or patches, its response to sunlight becomes a patchwork. A quiet region here, a whispering patch there, all depending on whether the local freezer is glassy or tiled. Now imagine the sun rising in the visitor's sky. Even far from the inner system, a little warmth can wake the sprinter ices. The first sign is a thin exhale of gas leaking from cracks and pores. It is not dramatic. Think of it as a slow, steady mist, a breath you can barely see when you step outside on a cold morning. That mist is powerful in a subtle way, because every departing molecule can nudge nearby grains loose or carry along tiny flecks of organic material. Over days and weeks, the mist becomes a ribbon trailing behind the traveler, the way a perfume lingers long after someone turns a corner. What kind of perfume are we talking about? The interstellar kind, blended in a quiet nebula rather than a lab. Complex organics can form on icy grains in deep space, built step by step as radiation rearranges simple molecules into richer structures. Those organics end up as thin coatings and tar-like patches mixed into the crust. When sprinter ices leave, they can sweep off a little of that organic frosting. The result is a mist with character. It might glow more strongly in certain colors. It might warm in a way that hints at a specific mix. To our instruments, it is a scented signature without the need for fancy symbols. The way the mist escapes is its own story. Some of it leaks through seams, where low gravity and thermal stress have opened hairline cracks. Some of it seeps through porous layers, like air sneaking through a bundle of straw. In both cases, the flow is gentle, the opposite of those dramatic jets you see on familiar comets closer to the sun. This is more like a humidifier running quietly in the next room. You do not hear it, you notice the air has changed. Because the visitor is moving, the mist never hangs still. The fresh gas meets sunlight and starlight, and the molecules start to break apart and recombine. Newly freed fragments pick up electric charge and get swept along by the surrounding environment, while the neutral stragglers drift until they collide with something or wander into shadow and freeze again. That dance gives the ribbon a layered look. The freshest part stays near the source, dim and tight. Farther out, where the gas has aged a bit, the ribbon spreads and thins. If you could timestamp every parcel, you would see the ribbon as a timeline. Recent exhale near the traveler, day-old breath farther back, week-old whisper fading into the general night. Not all locations on the surface join the exhale at once. Darker patches absorb more sunlight and wake first. Brighter crust stays asleep longer. Rough terrain holds shadow pockets that act like mini coolers. A crack hidden in such a pocket can keep sprinter ices alive well beyond their expected range, feeding the mist from a spot that would otherwise be quiet. This staggered awakening makes the ribbon uneven, with knots and wisps where local geography tips the balance. It is the difference between a single note and a chord played softly on a piano. The tune has texture. Now add the possibility of clathrate-like structures without using the technical term. Imagine cages in the water, ice lattice, that corral other molecules. Warm the cage ever so slightly, and the doors unlatch. The prisoners do not stampede. They wander out, adding to the thin flow. This mechanism is perfect for creating activity far from the sun, when water itself remains solid as stone, but still participates by letting the guests leave. The cages are generous landlords with patient leases. Here is the part that tickles the imagination. If the freezer came from a system with different overall chemistry, the list of sprinters and stayers may not match our usual expectations. Perhaps there is more frozen nitrogen than we are used to seeing. Perhaps there is a stronger presence of exotic salts that change melting points and release schedules. Those tweaks would change when the mist starts, how it smells to our detectors, and how long the perfume lingers. A cooler homestar would have allowed delicate ices to form and survive, so this traveler could be carrying a bouquet we rarely sample. All of this gentle outbreathing matters because it seeds the space behind the visitor with a trail that is both visible and diagnostic. It is a laboratory experiment set up by nature. A slow leak, a moving source, a changing light. Follow the ribbon and you learn which ices wake first, which organics hitch a ride, and how the crust reorganizes itself as sunlight works its way down. The lesson is not loud, but it is clear. In the alien freezer aisle, the quiet items tell the best stories, and they tell them by leaving a delicate scent in the dark as they pass. Chapter 7. Reading Color Like a Library Card. Spectral Clues. Open a beam of light the way you open a book, and words appear, not sentences made of letters, but patterns made of colors. When astronomers split light, they are not breaking it, they are filing it. A prism or a grating stretches a single white streak into a rainbow band, and across that band you find dips and bumps that act like stamped dates on a library card. Those stamps point to the materials that reflected the light, the grains that scattered it, and the gentle warmth the object gave off on its own. Telescopes are nosy accountants. Spectra are the receipts. There are two big kinds of color news we can gather from a wandering outsider and its wake. First is reflected light. Sunlight hits the surface and dust, then bounces back toward us. Second is emitted light. The object soaks up energy and re-radiates a bit as heat glow. Most obvious at wavelengths our eyes cannot see. Each carries signatures tied to stuff in the crust and in the drifting ribbon behind it. To keep this friendly, think of reflected light as the cover art and emitted light as the liner notes. With reflected light, you look for a tilt to the overall color and for small notches carved into the rainbow. The tilt tells you whether the surface tends to look redder or bluer than a neutral gray. A redwood tilt can mean a surface coated in complex organics or weathered by long stints under radiation. A bluewood lean can point to fresher, icier patches or very fine bright dust. Those little notches, the carved bits, are the real gossip. Different minerals and frozen compounds absorb very specific shades, leaving narrow bites out of the spectrum. Stack bites in the right places, and you begin to recognize a cast of characters. Silicate minerals with iron in certain roles, carbon-rich coatings, salty residues, and trapped guests in the ice. Now aim the same logic at the trail. Dust grains are tiny, but a crowd of them can tint the light of space itself. When you train your spectrograph just off the main body, you are listening for the choir rather than the soloist. If the halo and tail show a different tilt than the surface, that contrast is revealing. Maybe the grains breaking loose are lighter in color than the crust. Or maybe they carry darker coatings that the surface hides under a brighter frost. Either way, the trail becomes a moving sample tray. Here is where birthplace enters the story. A traveler raised around a quieter, redder star, likely formed in a gentler furnace. The ingredient list in that kind of neighborhood can lean toward minerals that favor cooler assembly lines and ices that tolerate long, deep winters. When that mix reflects our sun, it may keep a soft, warm tint, even at distances where local visitors would look more neutral. You can imagine those shades as luggage tags written in color instead of ink. Muted cherry for a long, cold nursery, pale rust for surfaces kissed by slow radiation, smoky gray for grains seasoned by time rather than heat. We are not painting an exact portrait. We are narrowing the family resemblance. Because Earth has air that loves to stamp its own water vapor fingerprints across any rainbow, ground observers play a careful game. They calibrate by watching standard stars with known colors. They subtract the sky's contribution, and they cross-check with space telescopes that do not have to peer through weather. Only after this laundry is done do the real colors stand up. It is the spectroscopic version of wiping fog from a bathroom mirror before you decide whether your hair is a triumph or a hat day. Color also has rhythm. As the visitor turns, different terrains roll into sunlight. A patch with darker crust can make the spectrum tilt redder for an hour, then a brighter stretch swings in, and the tilt eases. Catching those swings is like watching a planet's day in fast forward. For the trail, the rhythm is different. Younger dust close to the source can look one way. Older dust, farther back, can look another way, as delicate ices fade and organics take over the tone. Plot those shifts against time, and you get a travel diary written in hues. What about false leads? Plenty. A faint redwood tilt could be a side effect, of very small grains rather than a special coating. A notch that hints at one mineral might actually be a stack of narrower features blended by distance and motion. Even the angle between the sun, the traveler, and our telescope can add its own bias, making rough surfaces sparkle or sulk. That is why observers rarely claim a material from a single dataset. They repeat the measurement at multiple angles, they borrow time on different instruments, and they invite skeptics to poke holes. Science is the universe's quality control department. The stamp approved is hard won. Now for a playful what if. Suppose the reflected light from the main body leans moderately red, suggesting weathered crust, while the trail shows a slightly bluer shade, pointing to fresher grains. That could mean the surface is older toast, and the shedding reveals the soft bread underneath. Or flip it, the surface looks neutral, while the trail leans warm, hinting that organics ride off with the dust more eagerly than brighter minerals. Each scenario has different implications for how the crust is layered and how sunlight digs through that stack as the object approaches then recedes. Emitted light adds depth to the picture. Even a chilly traveler glows a little at longer wavelengths, and that glow's shape changes with grain size and composition. Fine, fluffy grains cool fast and show one kind of curve. Compact, glassy grains cool slower and show another. If the glow from the trail and the reflection from the surface tell the same story, confidence rises. If they disagree, the argument is productive, because it means the dust and the crust are not twins. In the end, reading color is not fortune-telling. It is evidence gathering. You collect rainbows, compare them, and ask which origin stories fit best. A quieter, redder star will not sign its name in block letters, but it can hint through soft tilts and specific notches that line up with materials raised in cold peace rather than hot bustle. The message is minimalist but clear enough for those willing to stare, subtract, and stare again. Next time, we will stop staring and start feeling the invisible rails themselves, chasing how magnetic fields sketch paths that eyes cannot see. Chapter 8, Magnetic Chalk Lines. Invisible fields, real effects. If space had a chalkboard, the sun would be the teacher drawing endless spirals across it. With every turn, a steady outflow carries invisible lines outward, curling them into a giant pinwheel that fills the planetary yard. These are magnetic tracks written into the solar breeze, and they are not decorations. They are traffic lanes for anything that carries electric charge. Particles feel those lanes as real as guardrails. Dust that picks up even a tiny bit of charge can sense them too, like dandelion seeds catching the pattern of a swirling courtyard. Here is the friendly version of the rule. When something charged moves through a magnetic field, it gets nudged sideways, not forward and not backward, but into a graceful curve. Small, light particles bend tightly, drawing tight corkscrews along the lines. Heavier, slower pieces draw looser arcs, sometimes barely noticing. A grain's response depends on its size, how much charge it holds, and how fast it is drifting. That trio turns the spiral field into a selective filter, sorting the ballet of motes without ever touching them. Space may be quiet, but it is not hands-off. Now picture those spiral tracks as hair strands on an enormous head. Most days, the strands flow smoothly. Then a traveler enters the salon, carrying a faint cloud of charged gas and dust. The cloud is not a wall. It is a comb with soft teeth. As it glides through, it can coax the strands into a brief part, a neat lane cut into the swirl before the breeze hustles everything back. In that moment, the local magnetic direction can lean, tighten, or relax by just enough for attentive instruments to notice. Cosmic hairdo adjusted, selfie taken, wind resumes. How would a foreign cloud do this gentle styling? First, by changing the balance of charges in a pocket of space. Sunlight and the surrounding wind strip electrons from grains and molecules, creating a mix of positive and negative players that are eager to dance with the field. Add even a thin mist of newcomers, and the effective stiffness of the magnetic tracks changes. Imagine a guitar string that suddenly meets a fingertip near the fret. The string still vibrates, but the note shifts. In magnetic language, ripples travel along the field lines, but their pitch and speed adjust inside the cloud. Downstream, a magnetometer might record a pattern that says, for a brief stretch, the strings were tuned a little differently. Second, by shepherding the charge dust itself, grains that have gathered charge on their sunlit faces do not just drift, they tend to spiral gently along the tracks, like cyclists choosing a bike lane over gravel. The smallest grains, feather-light, cling to the magnetic path most closely. Mid-sized grains flirt with both the magnetic lane and simple inertia, weaving like joggers who cut corners. The largest grains, stubborn as grand pianos on wheels, mostly ignore the lanes and keep coasting. That size-dependent routing can sculpt the cloud into a layered structure, a magnetic ribbon of fine dust braided within a broader mechanical plume. Instruments that sense faint light scatter might see a narrow, delicate thread nested inside a wider glow, the thread tracing the chalk lines rather than the straightest shortcut. This is not only a dust story. Radio waves passing through a magnetized cloud can twist in a measurable way. Think of radio signals from distant sources as neat noodles. As they slide through a pocket where both charge and magnetic direction change, the noodles pick up a spin. Compare the signal before and after, and you can tell that the spaghetti took a quick twirl in a hidden ladle. It is a quiet test, no fireworks, just a tiny rotation that says the chalk lines were combed for a moment. Planets notice too, in their own languages. Giant worlds with magnetic shields listen to the solar breeze like big wind chimes. A passing patch that tilts the field can tweak the tune those chimes play, sometimes adding a soft extra note to the radio chorus around a planet. It would be brief, subtle, and easy to miss unless you were already listening. Space loves an Easter egg. What about the direction of the part? The spiral field switches its lean in broad sectors as the sun turns, like a stadium crowd waving left, then right. If the visitor's corridor slices across one of those transition zones, the cloud can pin the part on one side more than the other, creating an asymmetry that maps neatly onto the path. Follow the bend with multiple spacecraft, and you could sketch the comb's teeth, a rise, a pause, a release. Drawn across millions of kilometers like a hairstylist's flourish, grain charging has its own quirks that add to the pattern. The day side of a grain can charge differently than the night side. Shadowed nooks on rugged fragments can trap stray electrons for a while. As the cloud turns, those uneven charges shift around, causing micro-tugs that alter each grain's dance with the field. The result is a living texture. The thread along the magnetic lane wavers and thickens, never quite the same from 1 hour to the next. If you could speed up time, it would look like lace knitting itself, and then unknitting as the wind and light take turns steering. Could all this be mistaken for ordinary weather in the solar breeze? Certainly. The sun's own handiwork sends ripples, folds, and kinks down the chalk lines day after day. The way to tell of visitors combing from a local gust is choreography. If the tilt and the dust thread march with the projected corridor of the traveler, keeping time as the object advances, the story gains weight. If the features wander off to chase unrelated gusts, you close the case and keep listening. The universe is generous with misdirection. That is half the fun. Why should we care about a temporary part in cosmic hair? Because those moments show how sensitive our neighborhood really is. A thin, foreign cloud can rephrase the magnetic sentences written by the sun, if only for a paragraph. That rephrasing sorts dust, tweaks radio songs, and gives us a tracer that outlines the hidden tracks draped across space. Earth is basically a rock that won the cosmic lottery. Part of the prize is front row seats to the biggest salon in the galaxy. When the comb passes through and the style changes for a heartbeat, you learn the cut, the curl, and the sway of an otherwise invisible design. And once you've seen the chalk lines, you cannot help noticing how often the wind writes, erases, and writes again. Chapter 9. Warm, where it should be mild. Thermal oddities. When astronomers say they see a cold object, they often mean they feel it, not with fingers, but with instruments that sense faint warmth the way your cheek senses a sunbeam through a window. Telescopes tuned to longer colors gather this quiet heat and turn it into maps. Those maps do not look like glossy photos. They look like weather reports for the dark, with gentle highs and lows where you might expect nothing at all. It is like finding a campfire's glow with your eyes closed, because the air on your face says, there, right there. Here is the trick. Even chilly stuff glows a little. A rock drifting in starlight absorbs energy and leaks it back out as long, lazy light. The amount of leak depends on how quickly the surface can move heat around and on how eager it is to radiate. Some materials are great at sharing warmth within themselves. Others hoard it. Some surfaces are happy to shed heat into space. Others cling to it like a blanket on a cold morning. Telescopes measure that attitude. Point them along the visitor's corridor, and you can sketch a thermal personality, pixel by careful pixel. Reports of tiny warm patches along a predicted route raise eyebrows precisely because most of space is boring at these wavelengths. You expect a soft background, then, suddenly, a little bruise of extra warmth that fades as if embarrassed to be seen. The first question is always the same. Did the sun do something dramatic? Sometimes, yes, but sometimes the patches appear too localized or timed too perfectly with the moving lane we are tracking. That is when talk turns to unfamiliar dust and foreign skins. Imagine grains with low conductivity, the thermal equivalent of thick mittens. Sunlight touches their sunward faces, and the warmth does not spread quickly. The lit side gets a bit toasty, while the shade stays stubbornly cool. Turn the grain, and the warmth does not chase the light right away. It lags like a sleepy cat deciding whether to move out of a sunspot. A cloud of such grains drifting together could produce a patchwork of hot dots that collective instruments read as a tiny heat island. The effect is small, but in the desert of deep space, a small oasis stands out. Scale that idea up to the surface of the traveler itself. If the crust is covered in dust that resists sharing heat, then sunrise on that world is a sharp contrast. Bright slopes that warm fast parked next to hollows that remain cold as a secret. The boundary between them can glow in a way that makes thermal maps look like a coastline at dusk. Tilt the object, change the angle, and the highlights crawl like lanterns on a hillside. You do not need a roaring vent to make the map sparkle. You just need stubborn material and patient light. Surface roughness matters too. A field of tiny ridges and pits acts like a city skyline in miniature. Sunlight pours into the alleys, warming pockets that cannot easily vent their heat, while sharp peaks radiate freely. From a distance, those pockets average into a mild but measurable boost. It is the urban heat island idea. Without streets or people, geometry alone traps the day a little longer. If the grains or crust came from a colder system, where growth favored porous, flaky structures, that geometry could be more extreme than we usually see, making the heat islands brighter than expected at surprising distances. Rotation adds a rhythm to all of this. As the traveler spins, the thermal map sweeps under the telescope's gaze. Warm up, cool down, warm up again. With familiar materials, the beat is predictable. With mittens for dust, the beat drifts. The peak warmth arrives a little after the brightest sunlight, then lingers into the local evening. That lag, measured carefully, is a signature of how grudgingly the surface moves heat around. It is a stopwatch test conducted on a world you will never touch. Now think about the trailing ribbon we have been following from chapter to chapter. If it includes a generous share of low conductivity grains, the ribbon itself can carry thermal punctuation marks. Freshly released grains near the source may still be sorting out their warmth. A short distance away, they find their thermal groove. Farther back, they cool faster than you expect. If they are tiny and fluffy, that aging process can paint the ribbon with a gradient. a soft, warm blush near the traveler, a neutral band midstream, and a faint chill in the far wake. Read correctly, that gradient tells you the grain sizes and their eagerness to trade heat with the vacuum. Detectors must be picky readers. Earth's air is warm compared to space and loves to elbow into the measurement. So some thermal work happens from high, dry mountaintops or from orbit where the atmosphere cannot photobomb. Calibration stars, careful scanning, and repeated passes help sort real patches from noise. If a warm smudge shows up in one scan, that is interesting. If it shows up again with the same shape and timing, that is a clue. If independent observers see it while the corridor passes by, that is a hint that someone lit a tiny candle where there should be none. There are delightful false alarms, of course. A small asteroid you did not expect in the frame can masquerade as a warm blot. A background galaxy with a dusty heart can intrude. Even the instrument itself can puff warmth into its own optics if a panel decides to sigh. But cross-checking is ruthless. Move the pointing, change the timing, watch the blot chase the predicted lane, and the imposters drop away. What remains is a pattern that marches with the traveler like a shadow that is not quite attached. Why does any of this matter? Because temperature is a translator. It turns invisible properties into measurable differences. Low conductivity dust from another sun would not send a business card, but it would heat and cool in ways that tell on themselves. It would make microclimates in the emptiness, little neighborhoods of warmth that drift in formation. And if we can map those neighborhoods, we can infer the grain recipes and the crust habits without cracking a single rock. There is something charming about finding heat islands in a place that ought to be all winter. It feels like catching the cosmos sneaking a cup of tea. No grand flares, no fireworks, just a quiet hush that glows a touch brighter than its surroundings. Next, we will pull the camera back and study the bigger architecture those glows sit within. The ribbons and shells drawn across the inner darkness like careful handwriting on black paper. Chapter 10, Architecture in the Dark. Ribbons, shells, and streams. If you could switch off the stars for a moment and turn up a soft black light on the inner solar system, you would see that the space between planets is not empty at all. It is threaded with a faint haze called the zodiacal cloud, a city-sized fog made of dust from old comets and shattered asteroids. Within that haze lie patterns, bands, lanes, and gentle swirls that only appear when you step back far enough. Think of it as calligraphy written on midnight paper. Most days, the handwriting changes slowly, edited by planets and time. But every once in a while, a fast traveler motors through and writes a flourish. That flourish is what we are hunting. A transient ribbon left by 3IATLAS curling around existing dust like a speedboat writing cursive on a calm lake. First, the baseline architecture. The zodiacal cloud is not a single uniform blanket. It has belts where asteroid families have shed debris, faint sheets from old comet trails, and broad rings that have settled into rhythm with planets. Jupiter, Saturn, and friends act like gardeners with rakes, tugging dust into subtle lanes as it drifts inward under the soft push of sunlight. Over years, tiny grains spiral sunward, crossing one slow resonance after another, and the planets tap them into order. The result is a set of traffic patterns that is ordinary only until you realize how tidy it is for a system made of rubble. Into this orderly fog swings an interstellar object on a one-time path, fast and decisive. It does not have to drop much material to make a mark. A modest shedding of grains, stretched along its track, is enough. The important part is geometry. As the traveler sweeps through, its path slices the zodiacal cloud at a slant, crossing background lanes, the way a skater cuts across frozen tracks. That slant matters. It creates intersections, and at each intersection, a small shock to the local calm. You can picture a wake forming, not like a wall of water, but as a folded ribbon, a front edge where grains are newly injected, a spine where the ribbon is densest, and a trailing edge where the structure thins back into the fog. Now amplify the picture with motion. The background dust is not parked. It is slowly drifting inward and processing around the sun in gentle loops, with each grain's plane tilted a little differently. The ribbon from our traveler drapes across those loops like lace over spinning gears. Where the lace lines up just right, density rises. Where it crosses at awkward angles, the feature fades. The result is a cursive stroke that brightens in segments, dims in others, then reappears as if the pen occasionally lifted off the page. From our vantage, those bright segments might look like short arcs that share a common curve, clues that add up to one longer sentence. Planets do not sit this out. Their slow gravity acts like a set of invisible shepherds, tugging portions of the ribbon into preferred lanes. Near a giant, the ribbon's spine can kink gently, a modest dogleg that points back to the shepherd's crook. Farther from any heavy hand, the ribbon relaxes into a natural curve set by the initial release and the low drumbeat of sunlight pressure. If the timing is just so, a segment of the ribbon can become temporarily trapped in a mild rhythm with a planet, circling the sun at a ratio that repeats over and over. That is not a permanent jail. It is a dance step. After a while, the partner changes, and the ribbon moves on. Shells are the quiet cousins of ribbons. They form when a wave of grains is released over a short span, and then disperses outward into a thin, nearly spherical layer. In the inner system, shells never stay perfect. The planets dent them, the wind frays them, and sunlight pressure stretches them. But for a while, you can catch the hint of a roundish dish, an echo of the moment of release. If 3I/Atlas shed a brief pulse of dust, perhaps as sunlight reached a particular patch of crust, a faint shell could appear like a soap bubble that never quite closes, drifting and thinning until it merges with the fog. Streams are different again, long-lived, narrow corridors usually laid down by repeat visitors that circle the sun. Our guest will not circle, but it can still sketch a proto-stream, a newborn lane that only lasts until the differential pushes smear it thin. Imagine a chalk line drawn across a busy sidewalk. For a few minutes, the line is crisp and people walk through it, dragging little bits away on their shoes. After an hour, the line is a rumor. A proto-stream from an interstellar visitor has that flavor, fresh, narrow, fleeting. Catch it early, and you can watch it unwind. How would we notice such delicacy? Not by a single image, but by choreography. Surveys that map the zodiacal light, the faint glow of sunlight scattered by dust, can compare patterns night after night. If a new arc appears and then slides forward along the projected path of the traveler, you take note. If the arc brightens when it crosses known dust bands and dims in the gaps, that is even better, because it means the flourish is interacting with the existing handwriting, not drawing over blank space. The cadence matters. A cursive stroke should advance with the visitor, not wander off to follow unrelated currents. There is a practical side to this plein air art lesson. Ribbons that curl around background lanes teach us how quickly fresh dust is sorted by size and steered by low forces. Kinks near giant planets measure the gentlest versions of those planetary tugs. Shells test how a sudden release diffuses in a real environment. Proto-streams reveal how long a one-time deposit remains coherent before the solar system's slow blender turns it into texture. These are the small print clauses of orbital life, hard to simulate perfectly and invaluable to watch. A playful thought to end. If the zodiacal cloud is the solar system's cursive, then 3I/Atlas is the guest who signs the guest book with a flourish and a loop on the end. Most people will never notice the new stroke. The glow is too faint and the night too bright. But for those who do, the flourish is a reminder that even a quiet visitor can change the handwriting for a while. And when the signature finally fades, the page still holds a memory of the loop, hidden in the thickness of a line, waiting for the next careful reader to turn up the blacklight and say, "There, do you see it?" Chapter 11. Surprise fireworks, off-calendar meteor. Most meteor showers are punctual. They show up on the same weeks each year because Earth plows through the same bands of old comet dust, like a train hitting a familiar patch of snow. Each shower has a radiant, the patch of sky from which the streaks seem to fan out, and each has a parent body, the usual suspect that shed the material in the first place. It is comfortingly tidy: calendar, radiant, parent, repeat. Then sometimes the sky shrugs and drops glitter on a random Tuesday. No forecast, no famous name, just a handful of clean, bright lines that fade before anyone can say, "Wait, what?" Those surprise streaks are the off-calendar kind, and they are catnip for sky detectives. The first clue is timing. Fireball networks and low-light cameras keep nightly watch, and when several stations record similar streaks within minutes or hours, they triangulate the paths. That gives you a point in the atmosphere where each meteor lit up, and the direction from which it arrived. Fold-in radar echoes that ping on fast-moving trails, and you begin to extract speeds before air resistance did its messy work. The speed and the path together let you rewind the motion, like a security camera tracing a visitor back through doorways to the street. If you can pull enough paths together, a radiant emerges. It might be faint, a suggestion rather than a billboard, but even a suggestion tells you where to look on a star map. From there, you estimate an orbit, how tilted it is, how stretched, and where it crosses Earth's lane. Known showers cluster around known orbital families. If the paths do not match any of those families, and the timing lines up with a corridor where our interstellar visitor has been threading, your eyebrow rises. Coincidence is always an option, but curiosity taps the microphone. What would an interstellar sprinkle look like to a watcher on the ground? Not a storm, more like a brief, quirky flurry. The streaks might appear a little faster than your usual sporadic meteors, arriving from a direction that has not hosted a radiant before. They could cut the sky at unfashionable hours, perhaps in the quiet window before dawn, when the part of Earth you stand on is facing into the stream, like a car's windshield meeting rain. A handful might flare more than once, a sign that the grains are lumpy or fragile, breaking in stages as the air squeezes them. Quick aside, meteors are nature's way of writing in cursive with sparks, and sometimes the handwriting has an accent. At this point, the hunt moves from spectacle to substance, if even a tiny fraction of those grains survive the plunge. And some do, especially the sturdier ones. They settle onto roofs, into gutters, and across polar snow. Collectors use magnets to tease out specks from urban dust, then pick through the catch for tiny spheres with smooth skins or fragments with fusion crusts, telltale skins melted by atmospheric sprinting. Antarctic field camps sieve wind-drifted layers for micrometeorites, each one a dot with a travel diary folded inside. Back in the lab, those dots become testifiers. You can examine their textures under microscopes and their elemental recipes with gentle probes that taste the surface without chewing it up. You can read how they heated during their fall, how quickly they cooled, and whether they carried entrained bubbles or layers laid down in some long-ago cold. You cannot label anything interstellar on one clue alone. Too many local sources can mimic the headline, but stack several oddities: a path that rewinds to a non-standard orbit, a timing that hugs the traveler's projected lane, grain textures that hint at slow formation in a deep cold, a mix of elements that leans away from typical asteroid crumbs, and the case begins to look less like a prank and more like a postcard. Even if the grains are too altered by the fall to shout their origin, the mere existence of an off-calendar sprinkle tied to the corridor would be a lesson. It would say, yes, a single fast visitor can seed Earth's skies with a brief, unique drizzle. It would underscore how porous the solar system is, how it accepts mail from beyond without asking for a return address. The delivery is not guaranteed every time. The geometry has to cooperate. The stream the visitor laid down must intersect Earth's path at just the right moment, and our planet must be there to meet it. When the timing clicks, the atmosphere becomes a sorting hat, deciding which flecks burn to nothing and which tiny survivors settle into the grand compost of world dust. Networks make these moments catchable. Amateur cameras on back patios, professional all-sky systems on mountaintops, meteor radars near quiet fields. They sketch a living map of streaks each night. Pattern recognition software flags clusters that do not match known showers. Human eyes check the flags because the sky is fond of false alarms. Satellites flaring, aircraft glinting, stray sparks from elsewhere. The real ones are surprisingly polite. They arrive, they write their brief lines, and they leave for us a small scavenger hunt. There is also value in the near misses. Imagine the cameras register a set of streaks that looks promising, but the ground teams find no survivors. That absence says something about the grains themselves. Perhaps they were delicate, fluffy, more snowflake than pebble. Perhaps they were salted with volatile material that made them flash at modest pressure and vanish like breath on glass. Knowing what does not reach the ground is as helpful as framing what does, because it tells you what the ribbon behind the traveler is made of and how it ages. Call it a cosmic pop quiz. Most of the time we study dust at a distance, reading color and warmth and gentle scattering. An off-calendar meteor sprinkle turns the study hands-on. For a day or a week, the sky passes a note to the ground, and if we are quick, we copy it before the custodian sweeps. A few grains in a dish may not look like much, but if they truly rode in with a one-time visitor, they are time travelers in pocket size. They might be postcards older than our solar system, written without ink, stamped without approval, and delivered by surprise fireworks on a night when no one expected a show. Chapter 12, Not Your Usual Comet, The Coma with a Twist. If you have ever watched a kettle rise from a calm murmur to a feisty steam, you already know the heart of a comet. Take a small, dark nucleus, warm it with sunlight, and the buried frosts begin to breathe. Gas seeps outward, dragging tiny grains with it, and together they form a fuzzy cloud called a coma. That coma is not a solid shell. It is a busy, expanding atmosphere that the comet grows for itself and then sheds to space. From the coma's edge, sunlight pushes dust into a broad tail, while the solar breeze and magnetic rails whisk the charged gas into a straighter, thinner tail that points away from the sun like an arrow that refuses to bend. In short, heat, breath, halo, tail, classic. But classics have variations, and an interstellar visitor is the remix. A local comet tends to follow a script, quiet far out, then a burst of activity as it crosses certain sunlit thresholds, then a dramatic show near its closest approach, and finally a graceful fade. The rhythm comes from familiar layers and familiar pores. The visitor may not know our rhythm. Its crust could be patched with zones that wake at unfashionable distances, like a person who drinks espresso at midnight and chamomile at noon. The result can be a coma that rises gently where we expected silence and then flickers in odd patterns when we expected a steady crescendo. Start with the way a coma inflates. Gas that leaves the surface expands into the vacuum and smacks into dust, giving each grain a lift before both rush outward. For hometown comets, this lift builds a symmetrical, fluffy hood around the nucleus, rounded on all sides with a soft sunward bump, where fresh gas pushes hardest. If the nucleus spins, that hood often carries faint, fan-shaped jets that repeat like a carousel as active vents rotate into daylight. An interstellar visitor might sketch the hood differently. If its vents are shallower, broader, or scattered by a different childhood of cracks and seams, the outward push can be even and whisper quiet, giving the coma a velvety smoothness. Or, if the vents are few and finicky, the coma can look patchy, as if someone dabbed light with a sponge rather than painting with a roller. Steadiness matters. Imagine a traveler that releases just a little gas all the time, like a kettle that never quite boils, but refuses to go cold. The coma then grows to a modest size and holds there, neither flaring nor collapsing, a self-kept micro-atmosphere. That steady state can make the dust tail look cleanly stratified. a ribbon whose thickness barely budges night to night. Now, flip the script. Suppose the release is irregular, a series of small sighs separated by quiet. Each sigh lofts a fresh shell of grains that drifts through the older cloud, creating ripples and arcs that telescopes catch as faint concentric features. It is the difference between a soft hum and a tap-tap rhythm on the window. The charged gas tail, the slender spear pointing away from the sun, is another playground for quirks. In the standard case, it is straight and impatient, adjusting quickly to every twist of the solar breeze. With an interstellar visitor, the mix and pace of gas release can change how quickly the tail reacts. A very gentle, continuous exhale can produce a thin, taut tail that looks like a thread pulled by an invisible hand. A spotty release can bead that thread with knots where new material floods in, each knot then stretched into a teardrop as the breeze whisks it away. To a time-lapse viewer, the tail would seem to breathe, as if the traveler were counting under its breath. Rotation adds theater. As the nucleus turns, any fixed vent sweeps through daylight and shadow on a familiar comet that makes fans that repeat predictably. On a visitor whose vents sit at peculiar latitudes or depths, the pattern could be offbeat. A vent that faces the sun for only a sliver of a turn might send a brief bright plume, then fall silent, carving a spiral in the coma that unwinds into the dust tail like a corkscrew drawn in chalk. Another vent might sit in a permanent dusk, leaking lazily without ever flaring. A metronome you barely hear until you stack images and watch the geometry straighten into meaning. There is also the matter of recoil. Every exhale gives the nucleus a tiny push in the opposite direction, a barely there thrust that can add up. On a local comet, we often see that push swing the rotation by small amounts or tweak the orbit in ways we can model. For a visitor, the map may be less familiar. If the vents open and close in an odd pattern, the pushes can tug the nucleus into a different spin rhythm over the course of weeks. That new rhythm feeds back into the coma's choreography, adjusting where fans appear and how tails load their material. Black holes are the universe's way of saying delete browsing history permanently. This traveler is more like opening new tabs when no one asked. Lighting tricks make the twist even twistier. When the sun sits behind the comet from our viewpoint, the coma's forward-thrown glow can sharpen a subtle sunward spike, a whisker that hints at fresh, fine grains. When the sun sits to the side, that whisker fades and layered shells stand out more clearly. A visitor with gentle, persistent release can shine more evenly across viewing angles, a soft lantern rather than a sparkler. A visitor with irregular release can turn into a flipbook of shapes: fan, spiral, puff, lull, new tabs, new tabs. So when we say not your usual comet, we are not dunking on hometown classics. We are noticing that this outsider's coma could be a study in minimalism or in syncopation rather than bombast. It might hum where others roar, pulse where others swell, or scribble faint spirals where others draw steady fans. And in that difference lies the payoff. The coma is a living transcript of the surface, the vents, the spin, and the way sunlight negotiates with a crust trained under a different star. Read the transcript, and you do not just learn how this traveler behaves, you glimpse the lessons it carried from its distant birthplace. Next, we will let the biggest bouncer in the neighborhood step into frame and see how a giant's gravity can sculpt or snag a passing flourish without ever breaking stride. Chapter 13, The Giant Doorman, Jupiter as Traffic Control. Imagine pulling up to a velvet rope in space. The music is the hum of the solar wind, the floor is a carpet of faint dust, and the bouncer is a striped world the size of a small personal myth. Jupiter does not need a clipboard. It only needs mass and an attitude. Anything that comes close, pebbles, dust, wayward snowballs, even whispers of gas, feels the invitation and the warning at the same time. Our interstellar traveler sails in on a one-time pass, but the trail behind it might not get the same freedom. Jupiter, can focus it, deflect it, or, in a few lucky cases, park a slice of that trail in a temporary loop, like a valet tag that says, "Hold this for a moment." Start with how a doorman works in space. Imagine a river of particles gliding past a whirlpool. Far away, the flow is straight. Closer in, the course curves. Jupiter's gravity bends paths inward on the way in and flings them outward on the way out. That inward bend is gravitational focusing, and it can sweep more particles into a narrow corridor than would have passed through otherwise. Think of Jupiter cupping a hand to funnel crumbs across a plate. For a drifting dust ribbon, laid down by 3IATLAS, that hand can raise the local density briefly, sharpening a faint feature into something instruments can actually trace. Not every crumb gets the same treatment. The tiniest grains, pushed firmly by sunlight, can dodge some of Jupiter's persuasion and drift on with a shrug. Mid-sized grains are more impressionable. They feel both the light and the pull, and their paths tighten into graceful arcs that can skim past the giant and carry a new tilt. The larger grains, the stubborn ones, take the bend full on. Some swing wide and escape with only a story to tell. Others loop once, twice, and leave. A rare few may slide into a temporary holding pattern, not a permanent orbit, but a slow dance that lasts from weeks to months before sunlight and geometry break the spell. Where would those slow dances happen? Picture a bubble around Jupiter where its pull dominates over the sun's. Inside that bubble, the doorman sets the rules. Particles entering with just the right speed and angle can find themselves in gentle loops that skim the outskirts of that domain. They are not prisoners, more like guests at an after-party who stay until the music changes key. During that interlude, the loop becomes a tasting platter. Samples from another star system hang around long enough that a prepared spacecraft could fly through with nets open. Space catering, courtesy of the giant. The magnetosphere adds another twist. Jupiter carries an enormous magnetic environment that captures charged particles and sets them racing along field lines. If a portion of the interstellar dust becomes charged by sunlight, those grains can feel a nudge into preferred lanes near the planet. The result is not a neat belt, more like a faint arc or patch where charged motes linger a little longer. Radio instruments could notice that arc as a subtle change in the chorus of waves around the planet. It would be a quiet signature that says, the doorman not only moved the guests, it hinted where they might mingle. Resonances are Jupiter's other favorite tool, the long game moves. In a resonance, a particle circles the sun in a rhythm that matches a simple beat with Jupiter's period. Each time the particle passes a certain point, Jupiter offers a small, consistent tug. The tug is tiny, but repetition is destiny. Over time, the rhythm either ejects the particle to a safer lane or shepherds it into a stable groove. A slice of the visitor's trail that drifts into one of these beats could be stretched into a soft arc that rides along for a while, a kind of borrowed chord in the music of orbits. The arc would not last forever, but it could persist long enough to map and maybe even sample. All this choreography suggests a delicious mission idea. Send a nimble probe to loiter just outside Jupiter's realm during the visitor's passage. Give it dust counters, tiny scoops, and a freezer that keeps its catches cold and clean. Feed the probe live updates from survey telescopes that track the densest folds of the ribbon. When Jupiter focuses a segment or builds a temporary loop, the probe dips in, sweeps through the hotspot, and backs away. You would not need a dramatic rendezvous with the visitor itself. You would let the doorman deliver a tasting flight to a predictable corner near the ropes. Sample returned by gravity's concierge service. There are practical payoffs. Captured grains caught in a slow dance give us more time to read their properties without the blur of high speed. The loop geometry also separates sizes, as the mid-sized and large grains are most likely to hang around. That natural sorting is a gift to science. Instead of sifting a mixed bag, instruments could analyze cohorts. Here is the crunchy set. Here is the flaky set. Here is the metallic sprinkle. Each group tells a different origin story about the traveler's crust and the environment in which it formed. Of course, Jupiter does not provide freebies without fine print. The same gravity that collects can also yeet, and yes, that is the technical term we whisper under our breath. A loop that looks inviting on Monday can unwind by Thursday if a small shift tips the balance. The magnetosphere can charge grains in ways that drift them out of reach, and the planet's radiation belts are a brutal neighborhood for delicate electronics. Any probe skimming the doorman's shadow would need a good shield, a careful plan, and a willingness to wave off if the dance turns rowdy. Still, the vision is hard to resist. An interstellar signature enters the hall. Jupiter leans in, and a sliver of that signature lingers in a predictable nook. We swing by, catch a handful, and leave with a menu from another kitchen pinned gently inside the sample box. Earth is basically a rock that won the cosmic lottery. Part of the payout is having a giant neighbor who can, on a good day, act like traffic control, and a maitre d' at the same time. Next, we will trade the doorman's grip for deep time and hold a single grain to the light, asking whether some of these specks are older than our entire planetary story. Chapter 14. Stardust Time Machines. Grains older than our sun. Hold a tiny speck in your palm, and you might be cradling a story that began before our sun ever switched on. That is not poetry. That is the odd fact of presolar grains. Long before the planets learned their orbits, dying stars and newborn stars were busy sneezing out dust. Some of those motes wandered the galaxy, drifted into the cloud that became our solar system, and somehow survived the heat and hammering that built worlds. Later, a few were locked inside meteorites like bugs in amber. When those meteorites fell and scientists cracked them open, the specks inside turned out to be older than everything else in the rock. Time travelers, hiding in plain sight. Earth is basically a rock that won the cosmic lottery. Turns out, the winnings included a handful of fossils made of star ash. How do we know these specks are ancient? They carry a telltale rhythm in the relative amounts of heavier and lighter versions of common elements. Think of elements as families and their heavier and lighter versions as cousins. In the smooth mixing pot of our solar system, those cousins usually show up in predictable proportions. Presolar grains break the pattern. Their cousin counts are skewed in ways that match the unique casting styles of different kinds of stars. Some resemble the ash of old red giants, others echo the fireworks of stellar endings. It is like finding handwriting on the grain itself that says, "Sent with love from a long-gone furnace." The minerals that play host to these messages are small and stubborn. A classic is a compound called silicon carbide, tough as a tiny gemstone, and happy to survive the long road from one star to another. Others are grains rich in graphite, which is one of the forms of carbon, and little diamonds that make the phrase cosmic bling suddenly serious. There are even silicate grains, the rocky kind, that slipped through the chaos intact. Each material is a different kind of time capsule. Some prefer the company of calm, slow outflows from aging stars. Others are forged in violent events. The galaxy has many kitchens. The menu shows up in our labs as a sampler plate the size of a pinhead. Reading these time machines takes patience and very gentle hands. One line of work dissolves a meteorite's more ordinary minerals, leaving behind the stubborn specks that resist the bath. Another approach is to tease out single grains from fine powders under a microscope, one glittering dot at a time. Once isolated, the grains meet instruments that can knock off atoms and count them with exquisite care, building a map of the heavy and light cousins across the surface. No equations on the page, just a pattern that whispers. I came from a place where the oven ran hot, and the chef sprinkled extra heavy cousins on the dish. Now picture the trail behind our interstellar visitor as a fresh delivery route for similar time capsules. If even a few grains from that ribbon ride down into our atmosphere and survive the sprint, they would be brand new to us. Not new in age, older than old, but new in provenance. We already have Priscilla grains that joined our solar system during its birth. A catch from the trail would be like an update from a distant branch of the family, a postcard from a kitchen we have not tasted yet. The message might confirm that stardust recipes are common across the galaxy, or it might surprise us with flavors we have never seen. Catching such grains is not magic. It is a scavenger hunt. High-altitude flights can skim the upper air with collectors that snag tiny particles as they fall. Polar regions are excellent trapdoors, where clean snow stacks year after year and preserves small visitors in tidy layers. A future spacecraft could even park in the predicted path of the ribbon, with blocks of gentle gel that slow dust without frying it, then bring the blocks home for careful picking. None of these methods returns a bucket. They return a pinch, but with grains this talkative, a pinch is plenty. What would we look for in the new haul? First, the same cousin patterns that announce a star-born heritage. Second, textures that betray a slow growth in cold, thin gas. Layered shells, onion skin structures, or tiny facets that grew face by face. Third, inclusions, the little seeds inside a grain that sometimes act as a birth record. If a speck from the trail carries a seed unlike those we have seen in meteorites, that alone would justify a victory dance in the lab hallway. There is a philosophical reward too. Presolar grains remind us that our story is a remix. The atoms in our bones were forged in furnaces we will never see, and some of the dust that swirled into our planet arrived with name tags from other suns. If the trail behind the visitor adds new examples, it strengthens a picture of a galaxy that trades ingredients the way neighbors trade recipes over a fence. Photosynthesis is plants' way of saying we invented solar panels first. Pre-solar grains are the cosmos' way of saying we had takeout long before you built a kitchen. Skepticism is part of the journey. Not every odd grain is ancient. Heating during atmospheric entry can blur the cousin patterns. Terrestrial contamination can muddy the message. That is why labs cross-check, repeat, and dare other teams to poke holes. When the pattern holds across multiple grains from multiple collectors, confidence rises. It is science's version of a group chat, but with fewer emojis and much more dust. Imagine the moment a researcher finds a speck from the new haul with a cousin pattern that does not fit any shelf in the current library. Not red giant, not known stellar ending, something else, perhaps a quiet, cooler star with unusual chemistry, perhaps a rare path through a binary system where two stars tug a growth zone into an unfamiliar temperature. We would not know immediately, but the clue would ripple outward, guiding telescopes to look for stars that could write such a signature today. That is the power of a grain smaller than a sand flea. It points across time to a furnace still burning somewhere in the dark. So yes, these are stardust time machines. They do not tick or talk. They do not have gears. They are postcards that carry their own postmarks in the arrangement of their atoms. If luck and timing let us collect a few from the wake of a passing outsider, we would hold in tweezers a message older than our sun, written without ink, read without words, and understood by anyone who has ever kept a keepsake from a loved one who lived before they were born. Next, we turn from keepsakes to the watchers themselves, the surveys and spacecraft that make all of this possible, and the clever filters that keep the signal from drowning in the noise. Chapter 15. Eyes Everywhere. Surveys, spacecraft, and citizen watchers. If the night sky had a security team, it would be ridiculously overstaffed. Mountaintop observatories sweep the horizon like lighthouse beacons. Robotic telescopes stitch together mosaics as calm as quilt makers. Spacecraft float above the atmosphere, staring without blinking. Small satellites race along like diligent bike couriers, and down on the ground, thousands of patient people point lenses and antennas at the dark, sipping tea while the cosmos tries its best to act casual. The modern sky is not a quiet meadow. It is a busy airport with very polite air traffic controllers. Computers never get bored. even when asked to find the one weird pixel in a sea of normal ones. Start with the new breed of surveys that live for repetition. Night after night, they photograph the same wide fields, building time lapses of everything that refuses to stand still. The secret sauce is cadence. Return often enough, and slow movers, fast streakers, shy glows, and abrupt flares, each sketch their own rhythms. A single image is a rumor. A season of images is testimony. These surveys do not chase beauty, they chase change. Think of them as librarians who reshelve the universe hourly, then throw a party whenever a book teleports. On top of the flood of pictures sit software pipelines that never sleep. The first layers handle housekeeping, remove the twinkle of our atmosphere, flatten the uneven glow of the optics, and subtract last night's background from tonight's scene. Only then does the fun begin. Deep learning filters. Those tireless pattern matches. Compare every dot, streak, and smudge with the library of what is normal. They are trained on years of sky, including the pranks the sky loves to play. Cosmic rays that splatter detector. Known, a glint from a wayward satellite. Known, a smudge from thin cloud drifting by. Known. After these usual suspects are marched out of the lineup, what remains are the shy anomalies that might be real. A faint arc that was not there last week. A warm patch creeping along a predicted corridor. A dust plume with an attitude. Because the night is global, the alerts are global. When a survey flags something interesting, a note pings across networks that connect observatories on different continents and in space. A telescope in a dry desert picks up where a coastal one left off at dawn. A spacecraft above the weather confirms or challenges the claim. Data pours into shared dashboards where human eyes still make the final call. There is a quiet charm in that. For all the clever code, we still lean in, sip the tea, and say yes, that feature has the right shape to be more than a trick of the light. Small satellites have become the agile scouts of this operation. Once upon a time, you needed a school bus to fly a camera. Now you can fit a potent sensor into something the size of a loaf of bread and send a fleet. One can carry a dust counter, another a thermal imager, another a radio ear, tuned to the whispers charged particles make. They can spread out along an orbit like beads on a string, turning a single snapshot into a moving stereo view. If a feature drifts along the lane where our traveler has passed, the string catches it in sequence, building a three-dimensional sketch out of time and perspective. It is like tapping a glass of water at different points to learn the shape of the ripple. Deep learning earns another round of applause when it comes to linking observations across instruments. A faint glow in infrared light might correlate with a peculiar polarization pattern in visible light and a nudge in the local charged particle count. Each by itself could be a shrug. Together, they form a sentence. Teaching machines to notice that sentence requires patience. Feed them examples, show them false alarms, let them argue with your assumptions, and reward them when they discover a subtle match you did not know to ask for. Computers do not get bored, but they do get better at noticing the cosmic equivalent of a whisper in a noisy cafe. Meanwhile, citizen watchers widen the net with charm and audacity. Backyard telescopes fitted with sensitive cameras keep watch all night, uploading frames to public repositories, where automated tools look for motion that does not belong to a known satellite or planet. Meteor networks, doorbell cameras for the upper atmosphere, triangulate streaks, and hand off the sky coordinates to the bigger facilities. Radio amateurs listen for faint reflections as meteors ionize the air, a clever hack that works even through clouds. When a call goes out for a coordinated watch along a predicted corridor, the response is not a handful of observers, it is a chorus. Some of the best discoveries begin with a message that reads, "I saw a thing," and ends with a pile of data that says, "Yes, that thing deserves a closer look." The hardware keeps evolving, but so do the habits. Archiving is not an afterthought anymore. Every image, every calibration frame, every quick look chart is stored and cross-referenced so that future questions can mine the past. The day you realize that an odd feature today has a faint cousin in last year's data is the day you send cake to the team that fought for proper archiving. Future you loves past you, who labeled the boxes. There is humor tucked into the grind. Operators give pet names to misbehaving pixels. Coders slip in comments like, "If you are reading this at 3 in the morning, go drink water." A quiet observatory cat becomes a mascot for the search for subtle tales. These small human touches matter because the work is both relentless and delicate. Stare long enough, reject noise, accept doubt, and celebrate only when the evidence insists on being celebrated. Space is stoic, people are not. The balance is healthy, and then there is the dream that binds the spreadsheets to the stars, building a living atlas of change. Imagine a sky where every odd ripple, every brief ribbon, every off-calendar spark is tagged in time and place, ready to be revisited when the next traveler sweeps through. The atlas would not only save us from repeating mistakes, it would make us faster at hearing the quiet first note of a new performance. Black holes are the universe's way of saying delete browsing history permanently. Surveys are the universe's way of leaving a very thorough changelog. Next time, we will turn the skepticism dial to maximum and interrogate the suspects that can fake a trail. Solar mood swings, cranky instruments, and sneaky local dust belts. The mystery stays fun only when the butler is not always the butler. Chapter 16, Red Herrings in Space. What else could cause this? Every mystery needs suspects, and space supplies them by the constellation. Before we pin a trail of oddities on a single fast visitor, we have to ask whether the scenery itself is misbehaving. Solar moods, fussy instruments, and local dust doing local dust things can all masquerade as clues. The plot thickens, but thick is not proof. Sometimes the butler is just a coat rack with great posture. First up, the star at the center and its many habits. The sun does not simply shine, it breathes. Over the span of years, its magnetic fields wax and wane, opening long-lasting holes in the corona that send faster wind streams billowing through the inner system. Where those fast streams crash into slower ones, they build rolling compression regions that can warm, jostle, and tilt the breeze for days. Shorter tempers appear as bursts that fling out dense shells of charged gas. Then there are streamer blobs, small packets that detach from delicate structures and coast outward like jellyfish in a current. All of these can brighten dust by shaking it, nudge magnetic lines into temporary kinks, and bump the thermal background just enough to raise an eyebrow. The way to sort this is with timing and geometry. If an anomaly shows up at the same solar longitudes on multiple rotations, regardless of where our traveler is, chalk it up to the sun's routine. If it follows the visitor's corridor instead of the solar calendar, keep the case open. Now the ground beneath our measurements. Instruments that age, stretch, and sigh. Detectors accumulate tiny scars from high-energy particles. Individual pixels get cranky and begin to overreact to light or underreact to warmth. Pointing systems drift as gears warm by a fraction, smearing faint features in ways that resemble tails and arcs. Even a filter can grow a thin film of frost or dust, imprinting a ghostly pattern that moves with the telescope instead of the sky. Good teams treat their instruments like athletes. Baselines before the season, checkups after hard nights, and scrimmages against known targets. They observe calibration stars and empty patches, rotate the instrument relative to the sky, and compare the same field with different cameras. If an arc turns with the hardware, it is artifice. If it stays nailed to the stars, it earns another page in the notebook. Spacecraft have their own gremlins. A satellite moving from sunlight into shadow can exhale a little heat that wanders through the structure and nudges a sensor. Reaction wheels hum and set up vibrations that print faint ripples on long exposures. Stray light sneaks around baffles and paints soft glows that look like halos if you do not catch them. Engineers build null tests to smoke these out. Take short exposures and long ones, change roll angles, throttle heaters, and see which features flinch. A real feature survives these indignities. A ghost evaporates like a guilty fog. Then there is the local dust, vast and underappreciated. The inner system holds bands from asteroid families, rings shepherded by planets, and ribbons left by ancient comet paths. A fresh collision in the asteroid belt can puff a new veil that meanders for months before blending in. A quiet comet can wake briefly, lay down a thin sheet, and go back to sleep, leaving behind a barely there haze that only shows under certain angles. Even dust trapped in rhythms with planets can brighten for a while when geometry lines up, mimicking a newcomer's flourish. To test this, researchers consult dust atlases built over years, models of resonant rings, and records of recent outbursts. If the feature overlays a known lane or matches a predicted resonance glow, the simplest explanation wins. The atmosphere above ground observers adds another layer of misdirection. Air glow ebbs and flows, thin clouds drift invisibly at wavelengths our eyes ignore but cameras feel, and temperature inversions create gradients that mimic gentle thermal patches. Meteorological stations, all sky monitors, and simultaneous observations from multiple sites help here. If a warm smudge vanishes when you move to a drier mountaintop or persists in space-based data, the verdict changes accordingly. Human habits can trip us too. Selection bias invites us to notice only those frames taken when excitement was high. Overfitting turns noise into narrative when a model has too many knobs. To fight these, teams lock in a plan before peaking. Which times, which fields, which thresholds count as a detection. They predefine what along the corridor means in distance and in time, so that the phrase does not stretch to embrace every hopeful blip. They split data into halves, train on one, test on the other, and they invite outsiders to rerun the pipeline on raw files. If a result survives fresh eyes and fresh code, it stands taller. Parallax and phase can also play clever tricks. The angle between sun, object, and observer controls how strongly dust forward scatters light. A small change in viewing angle can make a faint halo bloom or a tail shrink without the dust itself doing anything new. Geometry can even slide an apparent radiant for meteors by a few degrees, steering attention toward the wrong parent. The antidote is to compute the phase angle for every frame and, when possible, to watch from multiple vantage points. A real trail should maintain a consistent spine once you account for geometry. A phase artifact will puff and fade in lockstep with the angle, not the traveler. Background imposters round out the list. Distant galaxies with dusty hearts can masquerade as warm knots if they land in the corridor by chance. Defunct satellites can glint and write shallow arcs that look like slow-moving features in stacked images. Even the moon, from far off the frame, can throw a wash of scattered light that imitates a soft glow. Cross-referencing against catalogues of galaxies and satellite paths, masking lunar angles, and repeating the same field at a different time of month trim these pretenders away. When all these suspects have been interrogated, some anomalies confess and go quietly, others lawyer up and return for further hearings. A precious few sit through every test and still align with the traveler's route, in position, timing, and behavior. Those are the ones that justify stronger words, not certainty. That word earns its keep rarely, but confidence grown from subtraction. In mystery work, removal is creation. Strip away the sun's regular mischief, the hardware's moods, the local dust routines, the atmosphere's flickers, the geometry's illusions, and the background's photobombs, and what remains looks less like a coat rack and more like a character who truly walked through the scene. That is the sober way to keep wonder honest. The plot stays thrilling, but the cast list is accurate, and with the pretenders cleared, we can finally ask the speculative question with a straight face. If a real trail delivered ingredients across space, what could ride along, and what would it mean for worlds that like to cook? Chapter 17, Seeds on the Wind. Ingredients for Life Delivered. Picture the solar system as a kitchen that never closes. Planets are the big pots simmering on the front burners. Moons are the side dishes, and between them float crumbs, drips, and the occasional spice flake from far away. Our interstellar visitor is a courier walking through this kitchen with a satchel that may carry more than glitter. Not life, but ingredients. The difference matters. Delivery of building blocks is not delivery of life itself. Just as dropping groceries on a doorstep is not the same as cooking dinner. Photosynthesis is plants' way of saying we invented solar panels first. Maybe interstellar dust is space's way of saying we invented sample delivery first. What could ride along in that satchel? Space is surprisingly good at making complex molecules on the cheap. On cold grains, simple gases freeze into thin coatings. Starlight and radiation rearrange those frozen layers into richer stuff. Sticky, tar-like films, ring-shaped molecules that love to stack, small acids and alcohols, and fragments that, when warmed in water, can link into longer chains. None of this requires a lab coat. It only needs time, cold, a sprinkle of energy, and somewhere to sit. A visitor raised under a gentle, redder star could have built these coatings layer by delicate layer, then locked them under soot or ice. The result is not a recipe card. It is a pantry smear that still counts. The trip through space is harsh, but not hopeless. Radiation gnaws at fragile bonds, and ultraviolet light is basically cosmic bleach. Yet protection is everywhere if you are tiny. A grain wrapped in dark carbon-rich crust is like a traveler in a thick coat. A shard tucked inside a crumb of ice gets a winter jacket and a sun visor in one. Even a pile of porous dust creates a maze that shields a core from the nastiest hits. The outer layers sacrifice themselves, breaking and darkening, while the inner layers nap. Space may not be kind, but it is big. There are always shadows to hide in. Then comes the sprint through an atmosphere, which sounds like a death sentence, but can be more like a tumble onto a soft rug. Very small particles do not slam. They slow gently as they meet air high above the ground. They warm, yes, but only for heartbeats, and the heat cannot burrow deep before the particle cools again. Fluffy aggregates fare even better. They behave like dandelion seeds, drifting to a stop without much drama. Some are caught by high clouds and trapped in snowflakes. Others settle onto oceans, lakes, or damp soils that whisk heat away fast. A lucky few might even land during rain, riding droplets like tiny parachutes, and arriving at the surface already wet, which is a friendly start for chemistry. Suppose a pinch of this delivered material finds itself in a pond, or tucked into fine clay on a volcanic shore, or glued to a grain of sand on a tide line. The story that follows is not a spark of life on command. It is a slow workshop. Minerals can act like racks that hold small molecules still so they can try combinations. Wet and dry cycles act like breath, pushing bonds to form and break until something useful emerges. A delivered ring-shaped molecule could help stabilize a growing chain. A simple acid could become part of a longer backbone. A tar-like film could act as a tiny membrane that keeps a few helpful pieces close while letting the wrong ones wander away. No miracles, just patience and a lot of auditions. Here is a playful yet serious thought. If several kitchens across the galaxy tend to make the same pantry smears, then worlds might start from similar starter kits. That does not guarantee the same cuisine. One world will stir with strong sunlight, another with deep ocean vents, another with seasonal floods on muddy plains. But the shared starter kit lowers the bar from impossible to merely unlikely, which is a big step in a universe that keeps trying new menus. Earth is basically a rock that won the cosmic lottery. Part of that jackpot may have been a sampler pack falling from the sky in the planet's messy youth. We should keep our claims honest. Finding complex molecules on grains is not proof that life rode in. Life is not a collection of parts. It is a way those parts talk, copy, and adapt. A delivered sugar or acid does not carry instructions. It carries potential, Even if a visitor sprinkled our skies with a million tiny packages, most would land where nothing useful follows. Rocks are patient, chemistry is opportunistic, timing is everything. How would we tell whether a building block came from far away, rather than from local chemistry that learned to do the same trick? One clue is the relative abundance of heavier and lighter versions of common elements. The cousin counts that sometimes carry the signature of a different furnace. Another is handedness. Many biological molecules on Earth prefer one twist over the other. Dust made in space shows more of a fair coin flip, unless it has been processed in a way that nudged the balance. A third clue is structure. Layers grown in cold on a grain often look like onion skins or frost filigree under a microscope, not like crystals grown from warm solution. Stack these signs across multiple grains and you can begin to argue for a foreign pantry. There is also the ecological view. A rain of building blocks does not only feed the origin story, it can feed the continuation story. Modern Earth still receives a steady dusting of organics from space each year. Most becomes compost for microbes that already thrive here, which is delightfully circular. The galaxy delivers snacks to a biosphere that learned to snack on the galaxy. The same could be true, in quieter or louder form, on any world with air and water and geologic mischief. The fantasy version of this is panspermia, the idea that life itself spreads between worlds like hardy seeds. It is a bold idea with romantic appeal. The careful version stays one notch lower. What travels well are not seeds but ingredients, sometimes arranged in promising clusters that give local chemistry a head start. Space is a terrible nursery for living cells. It is an excellent wholesaler for the stuff that cells like to use. So if a ripple behind our visitor delivered even a spoonful of complex organics to a waiting shoreline, that is not a revelation that we were seeded from afar. It is a reminder that nature runs a shared market. Worlds shop there at different hours, pick different baskets, and cook different dishes. Some kitchens never light the stove. Some, like ours, throw a dinner party and invite oceans, air, and time. Next, after the flyby, we will ask what legacy remains when the guest is gone. The upgrades to our instruments, the maps we drew, and the way the sky looks slightly different once you know how to read its faint handwriting. Chapter 18, The Afterglow. What we learn when the visitor leaves. When a guest slips out the door and the music fades, the room is never quite the same. You notice scuffs on the floor you had not seen, a draft you did not know about, a note someone tucked under a glass. That is the feeling after an interstellar traveler sails on. Whether the rumored trail of oddities remains convincing or dissolves under tougher scrutiny, the real plot twist is what we keep. Sharper tools, better questions, and a calendar full of smarter watch shifts. First, the instruments. During the chase, every detector had to grow up a little. Cameras learned to hold focus through long, quiet exposures. Thermal sensors practiced catching the faintest warmth without flinching at their own breath. Dust counters tuned their ears to softer taps. Even software changed its gait, training on new patterns so that the next whisper does not sound like nonsense. That work does not evaporate when the object leaves. It becomes part of the baseline, the new ordinary. From now on, the sky will look crisper, not because it changed, but because we did. Second, the playbook. Early excitement makes teams quick. Later, audits make them wise. We retire habits that confused artifacts for features. We add cross-checks that compare wavelengths, angles, and times more ruthlessly. We simplify alert criteria so genuine oddities do not drown in their own paperwork. In short, we rewrite the first 10 pages of the manual, the ones operators flip through at 3 a.m, when coffee is an idea rather than a beverage. The next outsider will benefit from those pages more than from any one headline. Third, the map. We catalogue the places where faint glows appeared, where warm patches lingered, where the breeze forgot its manners for a minute. Even if some items are later demoted from intriguing to ordinary, the ledger matters. Patterns take time to reveal themselves. A single curve means little. A family of curves starts to hum. We will build a shelf labeled interstellar signatures and stock it with measured shapes, tones, and tempos. Some shelves will be crowded, others sparse. That is fine. A useful library is not orderly because everything matches. It is orderly because you can find what does not. Fourth, the questions. The best science fair projects are the ones that end with an index card that reads, "Things we did not expect." We now have a stack of those cards. How often do visitors carve brief ribbons in familiar dust? Under what angles do halos betray exotic grains? Which giant planet corridors make the best tasting rooms? When is a thermal dot a real heat island? And when is it a trick of geometry? None of these questions require the last guest to return. They require us to keep watching with the same persistence we brought to the chase. Fifth, the patience. Hype is a sprinter. Evidence is a marathoner. In the afterglow, we recalibrate our pace. We smile at the clips that oversold the mystery, and we print out the graphs that quietly earned their place. We accept that some clues are forever ambiguous. That is not failure, that is the universe reminding us how big it is. Curiosity thrives on maybe, as long as maybe is accompanied by habits that sift, repeat, and invite challenge. Earth is basically a rock that won the cosmic lottery, and the jackpot is curiosity paid out in installments. There is a community lesson as well. The chase braided professionals, hobbyists, and classroom skywatchers into one long antenna. A backyard station caught a fleeting streak. A mountaintop telescope confirmed a faint arc. A small satellite added a blip of warmth at the right moment. That choreography is not a one-time performance. Now that we know which steps mattered most, we can standardize them. Shared timestamps, common data formats, plain language checklists that let far-flung teams snap into formation swiftly. The next call for eyes will sound less like a scramble and more like a drill. And the public? Oh, the public, people who had never heard of dust forward scattering, can now explain it at dinner. Kids learn that sometimes the best result is ruling out the wrong answer with style. A few future engineers met their calling at midnight while watching a live stream of a patch of darkness that, for a heartbeat, refused to behave. Wonder is a renewable resource. The afterglow is where we harvest it. Even uncertainty has a neat trick to offer. It defines the boundaries of our models. If a trail feature evaporated under better data, it tells us how convincing noise can be and how to design filters that do not fall for the same magic trick twice. If a feature persisted, it tells us where our theory is too tidy and needs a wrinkle. Either way, we come away with edges that are more honest. So what do we do with a quiet sky once the guest is gone? We turn it into a training ground. We run mock alerts through the system. We sequence nights that replicate the geometry we just learned was persuasive. We preposition small satellites where the next corridor will likely pass. We keep our capture kits ready, our data rooms tidy, and our sense of humor intact. Space is a stern teacher, but it laughs kindly when we learn. Now for the tease, because stories do not end, they braid. Another outsider will glide through. It might be brighter, darker, quieter, or weirder. When it does, we will not start from scratch. We will open the catalogue of cosmic signatures and compare strokes, halos, tails, ripples, heat dots, radio twists. One traveler at a time, we will learn to read these autograph lines until the handwriting of the galaxy feels familiar. The mystery closes for tonight. The door clicks. The room exhales. And somewhere on the horizon, a new set of footsteps is already tapping softly toward the threshold.